Okay, all right. So let's start. So today's topic is common base amplifier, and this is how our discussion will proceed. We'll look at, as usual, the voltage gain, input and output resistances of a common base amplifier. And an important thing is we already know a common emitter amplifier, and when we are talking about another configuration, we need to ask questions: how does it compare? What are the advantages, disadvantages? And among the advantages of a common base amplifier, we'll see the frequency characteristics. But we'll see a lot of problems with the common base amplifier. And in an attempt to solve the problems associated with common base amplifier, take its advantages properly into account, we'll look at a amplifier which we call as a cascode amplifier. All right, anyway, so let's start with the common base amplifier. So the first question is, why do we need another amplifier when we have a common emitter amplifier? And in previous discussion, we saw that one of the problems with common emitter amplifier is that the gain, as you try to increase the gain, the 3 dB frequency, upper cutoff frequency, starts to fall. And among the reasons for why 3 dB frequency falls with increase in gain is when you look at the expression for the 3 dB frequency, one of the reasons is that this capacitance that you see here between base and collector, which is C mu, it gets multiplied by the gain of the amplifier GMRC dash here. So as you try to increase the gain, this capacitance which appears over here, as we saw through the Miller's theorem, that any capacitor connected between input and output port can be transformed into a capacitor at the input port or the capacitor at the output port here. And the capacitance which appears at the input port is this one here, C mu 1 plus GMRC dash. Now, if you recall the last lecture's discussion, we saw that the gain of an amplifier can be pretty large. If we take RC and replace it by an active load, we saw that gain could be 1,000 or 2,000. So gain, we can build up large amounts of gain, but note that suppose I design an amplifier of gain 1,000, and this is a small capacitor, 1 picofarad. But then 1 picofarad will get multiplied by 1,000 and will appear as a 1 nanofarad capacitor. So it will appear as a huge capacitor here at the input side here, and that will result in fall in the amplifier upper cutoff frequency. So that's the problem that we are looking at or addressing as to how can I get rid of this Miller's effect here. Miller's effect in this particular amplifier. And in that context, we said, let's look for an amplifier in which there is no capacitance between input and output port. If there is a capacitance between input and output port, that will always get multiplied by the gain of the amplifier. All right, so in that context, we said that if we look at a transistor shown over here, we see there are capacitances between emitter and base. We see there's a capacitance between base and collector, but there is no direct capacitance between emitter and collector. So with that motivation, we said, why don't we build an amplifier where we apply input at the emitter and take output at the collector. There is no direct capacitance here in between the two ports here. There is capacitance between here and there is a capacitance between here, but no capacitance directly between input and output. So this particular configuration for us will potentially not suffer from Miller's effect, and maybe we'll be able to break this trade-off between gain and frequency. That if I start building up very high gain, perhaps the frequency will not degrade due to the absence of a capacitance between input and output port. So that's one way of introducing a common base amplifier. It's being introduced as an attempt to solve a particular problem in common emitter amplifier here. As you can see here in this simple schematic that we have drawn is the earlier schematic that you were seeing was a vertical schematic. We have turned it 90 degrees. Here the biasing is exactly the same. There is R1, there is R2, there is RC, there is RE. It's the same biasing that we saw earlier. And the output is also taken from the collector in the same manner. There is no difference here. The only difference is that we have coupled the input from the emitter side. We have applied input to the emitter here, and the base we would, when we call it a common base, it's common base in the sense that under small signal analysis, the base is a small signal ground. Okay, so to ensure that, we've put a capacitor over here, so that when we do AC analysis, this point will become a small signal or a AC ground. And then, as you can see here, the base would serve as a common terminal. The input is being applied, then you can say is between the input, between the emitter and the base, the output is being taken from between the collector and the base. All right, so that's how it gets the name common base amplifier. All right, so having seen this, let's go ahead and analyze it. DC analysis, as I said, we don't have to do anything. It's the same circuit, same expression for ICQ, same VCC, same stability issue. If you want to make the bias point stable, same things you have to do here. No change. All right, so let's not spend time here. Let's do the mid-frequency analysis. So first, mid-frequency analysis, meaning we short out all the capacitors here, external capacitors. We leave out all the transistor capacitances, we open circuit them, and when we transform, we get a schematic like this here. Now, a little bit of confusing here in the sense that this is drawn horizontally and the schematic is, the equivalent circuit is turned 90 degrees here. But if you just take a look at it, you'll see that, yes, this schematic does correspond to this one over here. All right, note that R1 and R2 both drop out because both sides are ground. R1 and R2 both drop out. RC is ground over here. I've left RL is of course here, and between collector and here, between the collector and emitter, between collector and emitter, it is this GMVBE. So this point is our emitter. Between emitter and base is the ground. So we have R pi here, and we are applying signal Vs directly here. So Vs is over here. Okay. So so this is the schematic here, and I'm not going to sit down and derive it for you. You can see it very easily. If Vs is here, you can see that Vs is nothing but minus VBE. Vs is minus VBE. So this is simply the arrow will turn up. It will become GMVS, and GMVS flows through a parallel combination of RC parallel RL, and then that's where you end up with a gain of GM, RC parallel RL. GM we know is ICQ by V2. So if you look at this expression, you see the gain is exactly the same as, in terms of its magnitude, same as common emitter amplifier. Same gain, except that there's a positive sign. There's no phase shift. There's no phase shift between the input and the output. So there's a positive sign here. One should not forget that. So that's AV. And so same gain as common emitter amplifier. All right. Let's calculate the other things are output resistance. If we look at it, all right, before that, let's look at the input resistance here. So input resistance is the resistance seen by my source here, Vs. So the resistance seen by my source here, you can calculate and show, we'll see it in a minute, is R pi by beta parallel Re. And the output resistance that you see from here, output resistance seen by the load. So you ignore the load part RL here, and you look at it from here, and the current source offers a very high impedance here. There is an R0, of course, here, which we are neglecting for the moment. So all that you see is RC. You see RC here, so R0 is RC, Rn is R pi by beta parallel Re. How do I see that? Voltage swing is also similar. Okay, how do I see Rn? Well, let's look at this particular picture. Rn is the resistance seen by my source. So one, you can see here, this point is ground, small signal ground, obviously. So one resistance is Re, and then Re in parallel with resistance seen from the emitter. And we've already seen that when you look into the emitter, the resistance that you see is R pi by beta, especially when there is no resistance in the base. If there were a resistance in the base, you would have added R pi plus Rb divided by beta. So we know this R pi by beta here, and please remember this when we say this is the resistance between this node and ground. Whenever we are saying the resistance looking at a particular point, it's always between that point and ground here. So this R pi by beta is between this point and ground. Re is also between this point and ground. So obviously they are in parallel, and so Rn is R pi by beta parallel Re. And as you have seen by now that Re, when you are biasing, Re is typically large, and R pi by beta is very small, and therefore Rn would primarily be R pi by beta. R pi by beta, so it's going to be, so when you compare it to the common emitter amplifier, you are seeing that it's a small input resistance here. All right, sometimes we also calculate besides voltage gain, input resistance, and output resistance. Sometimes you'll see in books also calculations for current gain, short circuit current gain. So you take the output and you short it. So this is the current that flows in the output if you short the output here. So this is the current here. This is the current taken from the source here. And you can easily derive and show that the current gain is less than 1. Less than 1 because, you're forcing current into the emitter here and you're taking current out at the collector. The emitter and collector, the gains are less than 1 here. So anyway, if that's of interest, that also one can easily calculate here. All right, so let's summarize here. AV is ICQ by VT, RC parallel RL. Rn is R pi by beta parallel RE. R0 is RC. Okay. So if we look at this expression here, if for the moment, if I ignore RL and talk about open circuit voltage gain, AV0. So AV0 would be simply ICQ by VT RC. Or in general, you can say AV will always be less than this value. AV, ICQ, VT, because this term will always be less than RC, or it will always be less than RL. So anyway, I can write this. AV is ICQ, VT, RC, AV will always be less than this. Rn would always be less than R pi by beta. R pi by beta here and here, so I can write that, and R0 is RC. So what I can do is, with these simplifications, I can combine them up and show that AV, Rn by R0 will always be less than 1. If there can be situations where, for example, I don't have any RL, or Rn is, if I bias it through a current source, Re is very, very high, then I'll arrive at a value which is exactly equal to 1. AV, Rn by R0 is 1 here. So you compare this. Compare a common base amplifier, and you see that this is the expression for gain. Gain is just like common emitter in terms of expression. Input resistance, very small. Input resistance, if you recall, for a common emitter was R pi. Here it gets divided by beta, R pi by beta. So it's 100 times smaller. Output resistance is just the same expression here. So this is the, again, there is a trade-off, as you can see here. You can exchange gain with input resistance, and you can exchange input resistance with output resistance, which is summarized here. So there is a trade-off between voltage gain, input and output resistance, just like common emitter. So let's look at this expression here. Say I put a gain of 100. I design a common base amplifier. I can choose ICQ, I can choose RC and design it for a gain of 100. If this is a gain of 100, I choose a output resistance of 1K. Then I'll end up, if this is an equality, I'll end up with a input resistance of 0.01K, which is 10 ohms. So with that in mind, usually what happens is, if I say AV is 100, R0 is 1K, and 0.01K I get Rn, then very often in textbooks and other places you find that common base amplifier is summarized as an amplifier that can offer you high voltage gain. I can get a voltage gain of 100. Input resistance, low, in fact very low, and output resistance 1K, which is considered as medium here. But as I've been saying, that this way of summarizing an amplifier saying high, low, medium are not proper. You can obviously see from this expression, I can also design a common base amplifier with a gain of, or with an Rn of 1K, right? I can make Rn 1K, gain of 100. What will happen to R0? I will have to multiply Rn by a factor of 100. And so if this becomes 1K, then this will become 100K. I can also design like that. So it's not right to talk about a common base in this terms, but as I said, usually in books you will find this is how common base is summarized. So if you think of a common base amplifier versus common emitter amplifier, very often you'll see a table like this. A common emitter amplifier offers you high voltage gain, medium input resistance, medium output resistance. A common base, on the other hand, offers you high voltage gain, same expression we saw. Output resistance was also same expression. and input resistance is low. But as I said, these are not proper ways of summarizing. A better way of looking at common emitter versus common base are these two expressions. This is how a common emitter amplifier behaves in terms of its capability, AV, Rn, R0. And this is how a common base amplifier behaves with AV, Rn, R0 are less than or equal to 1. So a better comparison would be if I, let's say, design it in such a way that this is close to 1 and this is close to beta, then common base is here, common emitter is over here, and I can take a ratio. I can take a ratio of these two, and I get this. All right, so I can get this. Now, if I want to compare common emitter with common base, what are the things that I can say? This is a better comparison. This equation is a better comparison as compared to that table that we had. Table was a very specific case that we were dealing with. So here, if we look at it, we can say, well, suppose I design both my amplifiers to have the same gain. I can have common emitter and common base both having the same gain. This ratio is 1. I can design it such that both have the same output resistance. Then what will I find? That the input resistance of common emitter amplifier is larger than the input resistance of common base by a factor of 100. So one way of comparing common emitter and common base is, we can say, for the same gain and for the same output resistance, a common emitter amplifier is better than a common base amplifier because it offers us 100 times higher input resistance. That's one way of saying it. I can also say the same thing another way. I can design the two amplifiers such that they have the same gain, they have the same input resistance. I can make that. And in that case, we can see here, I'm assuming beta to be 100. R0 versus R0 of common emitter would be 100 here. So we can also say that for the same gain and for the same input resistance, a common emitter amplifier offers you 100 times lower output resistance as compared to a common base amplifier. So you can state it in that way also. And again, now you can play around with this and you can state the advantages of one amplifier with respect to the other in different ways here. But this is what summarizes it. The amplifier in terms of its gain, input, and output resistance. The capability of each amplifier you can see here versus the other is summarized in this particular equation. So, are there any advantages of common base? If you look at this. I mean, so what we are saying is if you look at AV, Rn, and R0, so we are seeing that in terms of gain, input, and output resistance, a common emitter amplifier is always superior. Is always superior because remember, for a voltage amplifier, what is it that you need? High gain, high input resistance, and low output resistance. These are the things that you're looking for. And in those terms, the common emitter amplifier is beta times, 100 times better than a common base amplifier here. So in terms of gain, input, and output resistance, we are not seeing any advantage. In fact, it's 100 times worse. Either the output resistance will be 100 times worse, or the input resistance will be 100 times worse, or if you try to make these comparable, then the gain will become 100 times worse. All right, so it's not a good voltage amplifier, a common base, as you can see from here. Okay. All right, so does it have any advantages at all? That's what we are asking. Okay, so in terms of gain, input, and output resistance, no advantage. In fact, it's worse. So let's look at the frequency response then. Okay, so I'm not going into the lower cutoff frequency. The lower cutoff frequencies, if you calculate, are comparable. Common emitter, common base. We saw that lower cutoff frequency is basically determined for common emitter by this emitter bypass capacitor. Here also there is this capacitor here. It sees similar kind of resistance. It sees Re, and then when you look into the emitter, you see same R pi by beta. So lower cutoff frequency is similar. There are no particular advantages. So what we need to do is look at higher cutoff frequency. All right. So higher cutoff frequency or upper cutoff frequency, we need to take this and transform it into our high frequency hybrid pi models. We need to substitute that. And when we look at upper cutoff frequency, what I've been telling you is that at many times we ignore the base resistance RBB, but that's central. In upper cutoff frequency, that plays a extremely important role, and you have to include RBB here. So you can see here, we have included RBB, RPi, CPi, CMU, the usual terms that are there. Even though this is there, initially we have been putting it, but later on we are ignoring this particular capacitance here, collector substrate capacitance. The usual things here, in addition to the source here, I've added, all sources will have some resistance RS. So we've added some RS here, and then there is an RE here. Okay, so this is the equivalent circuit of this particular amplifier. And the first thing to do is make things a little bit simpler. You can combine RC and RL and a few other things. So that's what we have done. We've called it RC dash, RC parallel RL. And I'm going to look at first a case where I'm driving my common base amplifier through a very small resistance here. That the source resistance is very, very small. A first case here where RS is sort of negligible. So I put RS almost equal to 0. RS equal to 0. So negligible RS is the case that I'm looking at. And in that case, note that Vs is directly going here. And if you recall, how do we determine the upper cutoff frequency? We said we take one capacitor at a time, like let's say we take CPi, and we remove CMU, and we find out what is the resistance seen by CPi. And we call that resistance RPi. Fine, and therefore we have a time constant RPi CPi. Then we remove CPi, and we put CMU, and we ask what is the net resistance seen by CMU, and thereby we calculate the time constant associated with CMU. We sum up the two time constants, and we take 1 over 2 pi, the sum of the time constants, and we get the upper cutoff frequency. So it's for that reason that you realize that when I say I have negligible RS, then to find the equivalent resistances, I have to remove the source also. So that's why we get this circuit here. Okay, we end up getting a circuit like this to calculate the resistance seen by CPi and CMU. I've also put from our previous discussion the equivalent circuit for a common emitter amplifier. Common emitter amplifier, which is not driven from the emitter, but which is driven from the base. So the source here would have been here, and we've removed it in that case also. So this is the common base equivalent circuit for calculating the time constants, and this is the common emitter equivalent circuit for calculating the time constants. Note, RE is between this node and ground, and so this is also ground, RE gets shorted out. So you compare the two. You compare this amplifier, this equivalent circuit versus this equivalent circuit. So you'll see that whatever resistance my CPi sees is the same that CPi will see here also, is the same. And whatever resistance CMU sees, the same thing will be seen over here. The two equivalent circuits are the same. And therefore, I expect that the frequency response would be the same. Same upper cutoff frequency as common emitter amplifier. The two equivalent circuits are the same. When, under what condition? When I'm driving it through a negligible RS. And if I do this simulation, take these two amplifiers, common emitter on the left hand side, biased in exactly the same manner, 22K, 2.2K and all that, same biasing here. This is being driven from the base side, is common emitter. This is being driven from the emitter side, common base. Same, look at same biasing, everything is the same. This gives you a gain of minus 110. This gives you a gain of 110. We saw that exactly the same gain for same biasing, same gain here. Look at Rn, 2.2K, and Rn for this is 10 ohms, close to 10 ohms here, much smaller. R0 is 2.2K, R0 is same, RC here. And anyway, so this is there. If I calculate these are from simulation. If I calculate the upper cutoff frequency, 5.8 megahertz. If I calculate the upper cutoff frequency, 5.8 megahertz. Okay, same. So at this stage now, let's say common base amplifier has not been invented. Okay, common emitter amplifier has been invented, and you are the inventor of common base. You've come up with this idea of let me try and drive my amplifier from the emitter. It's a new configuration. So you have invented the common base amplifier. And this is where you are. What would you do? This amplifier already exists, right? Common emitter already exists. And you have now invented a common base amplifier. You're very excited, new configuration. And after you evaluate it critically, And this is what you see. What will you do with it? What is your judgment? This is what it is giving. Gain 110, Rn very low, R0 same, upper cutoff frequency same, lower cutoff frequency same. What will you do with it? Should we go forward with it or should we ignore it now? Should we ignore this amplifier? Should we ignore it? It's useless. I mean, this amplifier on the left outperforms the one on the right in every aspect, right? Gain is the same, fine. Input resistance is 100 times better. Output resistance is the same. Well, unless you care that this is minus and this is positive. If that is important, a phase shift is important for you, maybe you'll say, well, this gives me a zero phase shift amplifier, maybe, if you can think of that. But if you look at this versus this one is clearly better. This one is clearly better, right? So, what do we do with this now? Huh? Lower cutoff frequencies are comparable. See, 10 microfarad I've put here, 10 microfarad I've put here. What is the net resistance seen by this 10 microfarad here? Would be 0.56K in parallel with R pi by beta, similar. Lower cutoff frequency would be similar. So the issue is, what do I do with an amplifier like this? Is the point that I'm trying to make is a very general point. Let's say something A exists, and you know that there is a default solution that is already there. You come up with a solution, some solution B, and you start comparing, and you're seeing, well, this is what it is. Most of the things are similar as A, and in some aspects it's worse. It's very easy to get discouraged and throw it away. Forget about it. You know, there's no point. There's no point in going further. And that's a mistake. Many times you have to dig deeper and see, is there under any situation where this can offer an advantage? You have to start exploring. Maybe there is. We have not. Right now, you see the comparison is where I'm driving this amplifier through a negligible source resistance, and I'm driving this amplifier through a negligible source resistance. And then the comparison is being done. Maybe there is a situation, maybe I can get into that, where under that situation, perhaps this outperforms this in some respect. Okay? So right now, everything is the same, but one of the things that I've been saying is, I'm driving it with a negligible RS here and a negligible RS here. Let's change that for a moment. Okay, so as I said, simulation results show the same thing here. So the next thing that I did was, we put an RS of 2.2K here. And we put an RS of 2.2K here. Alright, look at what happened. First, the common emitter. When I put an RS here, the first thing that you see is the gain has dropped. Everybody agrees, gain will drop. Why? Because note that part of VS will get dropped across RS, and only a fraction will appear over here, and therefore the gain will drop. Okay, so the gain has dropped from 110 to 30. The upper cutoff frequency has also dropped, 1.76. It's also dropped. Why? Because the capacitors now see a larger resistance RS. Now, go to common base. Same amplifier, we put 2.2K. Well, earlier it was giving me 110. Now the gain is giving 0.48. 0.48. Why has this gain dropped so much? Why has it dropped so much? Because its input resistance is so low. Its input resistance is so low, so when I apply 2.2K, almost the entire voltage is getting dropped across 2.2K. Nothing is going into the amplifier. Input resistance is so low. It's a voltage divider. And therefore, it's 0.48. It's not amplifying at all. But are you seeing something positive? Hey, it's not amplifying, but it's 61 megahertz. Something strange has happened. That instead of this one is losing its value, I mean, it's losing upper cutoff frequency. This is 61 megahertz. But then you may still at this stage throw it away. Because you say, what good is an amplifier with a gain of less than 1? So by putting an RS which is higher, which is large RS, I'm getting a very high cutoff frequency, but it's useless. I mean, what can I do with such an amplifier with a gain less than 1? So again, that's what I'm saying. In the invention process, at many points you face situations like this and you see, well, there's nothing good about it, gain less than 1. And many times if you read the history of inventions, the way that has gone, a lot of people have seen interesting results and they've thrown it away. Somebody looked at it and carried it forward and eventually took the idea forward and then became the owner of the idea. A lot of people see it, but they ignore it or they throw it away. So that's what I'm trying to tell you here. Here, AV 0.48, upper cutoff frequency 61 megahertz. There'll be a strong temptation to throw it away. It's useless. I mean, yes, it's giving me 61 megahertz, but doesn't give me gain. An amplifier which attenuates the signal is no good, right? All right. Why? So this is what is shown by simulation here. You can see that this is our common emitter amplifier, and this is our common base amplifier here. Frequency response. So this is in red is the gain versus frequency of the common emitter, and this is the gain versus frequency of the common base here. You can see the scales are different. The gains are less than 1 here. But there's something very positive about it, which is it's a small gain, but it remains flat over much larger range. Okay, so what is really happening? So now, remember when I put a source resistance here, so what happens is the source resistance, so before that, what is really happening? So when I put a source resistance that you see here, go back to the equivalent circuit. When I put a source resistance here, large source resistance, then what would happen is I'll not go here. What I'll end up when I remove Vs, Rs will come in parallel with Re. Okay, there'll be a resistance here, Rs in parallel with Re. While in common emitter, there will be no resistance here. Are you seeing the difference? When I put a source resistance Rs which is significant, then Rs in parallel with Re will appear over here at this point. This is no longer ground, this is Rs here. And Rs in parallel with Re will appear at the emitter. While here, the emitter resistance is bypassed to ground, so there will be nothing here. So a changes occur the moment you put significant source resistance here. So with that, let me talk about, suppose we have a circuit like this, and this point is not connected to ground as was earlier, but let's say some resistance Re. What is the net resistance seen by C pi? Well, there's a little bit of calculation involved. I'll not go over it. Net resistance seen by C pi. You can practice your circuit analysis techniques on this. Go ahead and do your KVL, KCL, or whatever. Arrive at this. And so this is an expression that we get, large expression. But important point is the following: if I make Re large, this R pi, the resistance seen by C pi, is 1 over Gm. 1 over Gm. Resistance seen by C pi here. 1 over Gm, what do you know about 1 over Gm? It's a very low resistance. Okay, so the C pi is a very large capacitance. C pi is one of the dominant capacitances here. When you put a very large Re, then the C pi sees effectively 1 over Gm as a very low resistance. Under this configuration, the C mu, when you put very large Re, sees the resistance RBB plus RC. There's no Miller's effect. There's not this thing here. So when you put large Re, both the resistances seen by C pi and C mu go down. This comparison will show you. So in very large Re going to infinity means what? It's like an open circuit. Okay. So here is a case where it's ground, which was the situation earlier. Now I'm saying, suppose we drive it and design it in such a way that Rs is very large, Re is very large, so almost like an open circuit. Idealistic situation, extreme case here. So here, when I see R pi is RBB, parallel R pi, in this case, the capacitance, the resistance seen by C pi. In this case, the resistance seen by C pi is 1 over Gm. 1 over Gm. Now, note that this resistance RBB parallel R pi, in many cases, R pi would be much larger. And so R pi, this capital R pi will be equal to RBB, which for us is 200 ohms. So you have 200 ohms here is what the CPI sees. And here 1 over GM is 10 ohms. So 20 times smaller. The kind of resistance that CPI sees here. 20 times smaller. Compare the resistance seen by CMU. Here it sees RBB 1 plus GM RC dash. Note that RBB is getting multiplied by here. This is the resistance seen by here. And the resistance seen by CMU is simply RBB plus RC dash. So what is really happening is when you put a very large resistance that shows up in the small signal model between the emitter and ground, what you are ending up is getting the resistances seen by CPI and the resistance seen by CMU become very small. And that's the reason why you end up getting the time constants become small, and that's why you get very high cutoff frequency. Now, these are calculations as to, you derive it from KVL and KCL, you derive these relations. Think about why is the frequency response becoming large in terms of maybe, all right, I'll leave that for you to think about. What is the real reason when I make an open circuit, why is the resistance is becoming small here? So anyway, what we are finding is the following. That when you make the emitter resistance very large here, then the cutoff frequency is CPI by GM. That's the time constant associated with CPI, and CMU RBB plus RC dash. Cutoff frequency becomes very high. There's no Miller's effect. All these advantages are coming. When are they coming? When you drive your common base amplifier through a very high resistance, and the emitter resistance that you have here, RE is also large and RS is also large. Both of them are very large. And so large that it's practically, we are saying it's like an open circuit. And then the upper cutoff frequency becomes very high. So common base amplifier can provide you with very high cutoff frequency under very specific situation. And what is the situation? That the net resistance between the emitter and the ground has to be very high, which will require a large RS and a large RE. All right. So this is what is shown over here. But so I can take a common base amplifier here. Note that what I've done is, since we require a large RE, if you go back and I'm saying I require a large RE. So what we have said is, well, let's bias it through a current source. If I bias it through a current source, its small signal resistance is infinite, very high. Fine. That's why you see the current source here. And I need a large RS also. So I've connected a 10K. Why? Fine. And when you look at that, when you look at this amplifier under that situation, it gives us a upper cutoff frequency of 73.5 megahertz. But as I said, no gain. 0.1. So what we are seeing is that common base amplifier can give you the positive thing about common base amplifier that we are seeing right now is that under this situation, look at this situation here. Biased through a current source and also or very high RE and driven by a very large source resistance. Then your upper cutoff frequency is very high. But when you drive it with a very large source resistance, then what happens is all the Vs that you see here gets dropped here, very little goes here, and that's why the gain is not there. So this is the situation that we are in. We finally found some advantage of common base amplifier. We found that under this condition here, common base can potentially offer, note here, very high upper cutoff frequency. Now, what is the disadvantage? Now, if you want to take advantage of this very high upper cutoff frequency, somehow you have to address this. Why is the gain becoming so small? The gain is becoming so small because the input resistance is so small. Input resistance is so small and everything is getting dropped across RS. All right. So at this stage, so this is sort of a summary that you can see. All right. It just summarizes the whole thing here. So at this stage, I mean, you know what, one is in a dilemma in the sense that, yes, I'm getting higher FH, but I'm not getting AB. And, I can't do much. I mean, either I have to change the configuration because the advantages that you see here or FH and all are coming because I'm driving it from the emitter. That's the reason why it is coming, because I'm driving through the emitter. And emitter must have a large resistance to make the time constant small. But then when I drive it from the emitter and when I look into the emitter, I will always see a small resistance. I can't do anything about it. Okay, so at this stage, let's look at why do I want a small resistance, input resistance. Look at this common. So sometimes, certain things we take for granted. Voltage amplifiers, we know we require high input resistance, low output resistance, all that gets stuck in the mind, and we're always looking for that high input resistance, low output resistance. Why do we really want it? Well, because we are trying to make a voltage amplifier, right? So here is a voltage amplifier. Yeah, and you know that there is an RS, there is an RN, AV0, VIN, R0, and all that we saw right in the beginning of our discussion. And when we look at the overall voltage gain V0 by Vs, we can write it in this form. And we look at this expression and we say, if you want large gain, well, I need to make Rn very large, Rn much larger than Rs. Rn much larger than Rs, then this factor becomes close to 1. And I want R0 much smaller than RL, this factor becomes close to 1, and I'm able to get the gain that my amplifier is capable of, AV0. That's the highest gain that my amplifier can give. And that's the reason why we look for Rn much larger than Rs. That's a voltage amplifier. But suppose I don't drive it through a voltage source. My signal is a current source. Signal is a current source. So, for a moment, don't say that you're interested in V0 by Vs for a moment. Let's say you're interested in V0 by Is. Why is this a current source? When can I call my signal a current source? Well, when the resistance in parallel with it is high. When the resistance in parallel with it is high, then maybe it's more appropriate to call it a current source, especially when the resistance is high in comparison to the rest of the circuit. So if you have this situation and you look at V0 by Is, well, we can transform it. So when you are interested in V0 by Is, it's not voltage amplifier. It is voltage by current. It's voltage by current that I'm talking about, that I'm interested in. So we will call it voltage by current as a trans resistance amplifier. V0 by Is is resistance. V0 by Vs is gain, voltage gain. But V0 by Is is resistance, units of resistance. And because V0 is at the output port, Is is at the input port, there are two different places. We add the word trans. So we have a trans resistance amplifier. So in this case, if I were to write V0 by Is and write it in this form, in this case, what kind of an input resistance are you looking for? See, this is the current here. What do you want this current to do? You want this current to go entirely into the amplifier? Right? You want this current to go into this amplifier? What will ensure that this current will go into this amplifier if the input resistance is very low? Look at that. Rn is very low. So if Rn is very low, then this entire current that you have will go into the amplifier and then of course gets amplified and all that appears at the output. So if you have a trans resistance amplifier, if you're trying to make a trans resistance amplifier, you are looking for a very low input resistance. A very low input resistance here. And you are seeing that what does common base offer? A very low input resistance. So maybe I'm looking for the wrong thing from a common base. I'm trying to make a voltage amplifier through a common base. It's not suitable. It has very small input resistance. Maybe what I should look for is build a trans resistance amplifier where my input is a current. And if I try to do that, then my common base amplifier can be very useful. It will give me a large Rn. I mean small Rn, and therefore V0 by Is would be a high quantity. So I'll get a gain from gain, but it's not voltage gain, it's the trans resistance gain. It's V0 by Is that I may get high. So I was looking for a voltage amplifier. I'm not getting a very good voltage amplifier. I'm getting a good trans resistance amplifier. Now, if you say, well, I'm interested in voltage amplifier. So yes, it's giving me trans resistance, so I'm not interested. Should I throw it away again? Let's say I'm trying to design something and I'm interested in voltage amplifier. It's not giving me a good voltage amplifier, but it's giving me something else. Trans resistance amplifier, maybe is good for that. Should I throw it away? Well, yes, I'll keep it at the back of my mind. If I see a need for a trans resistance amplifier, I'll use it there. But for voltage amplification, should I throw it away? Should I throw it away? All right, so this is one of the conclusions that I get here. All right, so what we are saying is you drive it with a current source here, and all that I said, if you drive it with a current source, we can calculate what is V0 by Is, and all of that we can do. Okay, but note that we are interested in voltage amplifiers. We don't have a current source as an input. Our input is what? A voltage. We are interested in making voltage amplifiers. So should I ignore it and throw it away? Well, that's what I said. Many would throw and ignore it. But those who are patient and think a little bit more may look at the following. What does a common emitter amplifier do? Did we build this equivalent circuit? Did we show that if you look at a common emitter, this is a common emitter configuration because you're applying input at the base and taking output here. Okay, we said if you apply Vs here and look at it from the collector, if you look at this common emitter configuration from the collector, what do you see? Gm, Vs and R0, right? How large is R0? Very large. So when you see from the collector side, what are you seeing? This is a voltage source. This is a voltage source Vs. When you look at it from the collector side, what are you saying? Are you saying that common emitter configuration is converting a voltage source into a current source? It took a voltage source and converted into a very good current source. This is Vs and this is a current source, GMVS. Why is it a good current source? Because the resistance in parallel with it is very high. R0 is very high, 100 kilo ohm or so. All right. So now can you think of something else? I have a common base amplifier which is very good if you drive it through a current source. If you drive it through a current source. But I don't have a current source. I have a voltage source with me. I'm trying to amplify a voltage source. So are you seeing a strategy? I can take my voltage source, use a common emitter stage to convert it into a current source and then drive that current source into my common base. Maybe it's still useful. All right. So that's the strategy. A common emitter amplifier, one way of saying is a good voltage to current converter. Takes a voltage here and gives you a good current source. So maybe, how about this strategy? That we take our input, apply it to a common emitter, which will convert it into a current and feed this current into a common base. And we know that common base does what? A good conversion of V0 over I. It's a trans resistance amplifier. So how about trying something like this? Will it give us some interesting things here? So our conclusion for today is common base by itself as a voltage amplifier is not very good because of its very low input resistance. But if we drive common base through a current source, it can give us very high frequency, very high upper cutoff frequency. But I'm interested in voltage amplifier. So our strategy is take this common emitter stage, convert it into a current, feed it to a common base and arrive at a voltage. And what we want to do is see that if I do this here, will I get something interesting? And this configuration that you see here, a combination of common emitter and common base is what goes by the name Cascode. It's a very, very popular configuration. And next lecture we'll see. So this is what we are looking for, as you can see here. A common emitter stage here. We are feeding it here. And at the output is being fed here through this one. A common base stage. All right, so let's leave it and discuss it next lecture.